In the name of Allah, the Beneficent, the Merciful. Welcome to the world of physics. Due to coronavirus, we have to continue our online class. At first, I'd like to suggest you, stay home, stay safe. Let me introduce. I am mUKDADIR lecturer, Department of Physics. At first, observe this diagram. Actually, this is our third lecture and all of you already introduced with this diagram. This is the diagram of a transistor. And here the block diagram and circuital diagram of transistor is shown. And previously we also have discussed about the direction of current, that is and the equation for PNP and NPN transistor. And this is a block diagram and circuital diagram of PNP and NPN transistor. And here the basic difference of PNP and NPN is the direction of current. And in NPN transistor, here the carrier conducted by electron, and in PNP transistor the carrier is used as hole. And here the name of the chapter, if you know, the name of the chapter is Modern Physics and Electronics, and this is our third lecture. And today we are going to learn about, and after this lesson you'll be able to explain and you can draw the diagram of the common emitter, common base, common collector transistor, and operating point of transistor, and you can write the necessary equation of this chapter. Here, first, we are going to discuss about the common three common connections for a transistor. There is common base, common emitter, and common collector. Here, in common base connection, here base and base emitter connection is in forward base, and collector emitter the circuit is in collector base is in reverse direction in reverse base. And for common base connection, we have a current amplification factor that is shown, that is denoted by alpha. And the definition of alpha is the ratio of the change of the collector current to the change of emitter current. And here the connection is common base connection. And for common base connection, we have current amplification factor, that is alpha, is equal to del IC divided by del IE. It's for AC current, and for DC current we can write the equation, that is alpha is equal to IC by IE. And the expression for collector current, that is IC. Here in the last line we have the equation for collector current, that is IC is equal to alpha IE plus ICBO, that is leakage current. And total current is IE, and it comprises with IC and IB. And finally we have the equation, that is IE is equal to IB plus IC. And for collector current, previously we have this equation, that is IC equal to alpha IE plus ICBO, that is, and we put the value of IE in this equation. Then we have the equation, that is I is equal to IB plus IC. And by putting this value and after multiplication with alpha, we change the side, and finally we have a equation for IC. There is the expression of collector current. IC is equal to alpha divided by 1 minus alpha into IB plus ICB divided by 1 minus alpha. And characteristics of common base configuration for different different voltage, common base voltage, we have the input characteristics of in common base connection. Here voltage in base emitter junction versus IE is characteristics called input characteristics, and IE increase rapidly with the increase of VVE. It means input resistance is very small because we put the input circuit is in forward direction, and IE is almost independent of ICV, and emitter current doesn't depend on the common uh, uh, IE doesn't depend on collector base circuit. It's only dependent on base emitter circuit, that is input characteristics. And here the output characteristics, that is uh, uh, I here VVC, that is base collector voltage versus collector current, is called output characteristics, and IC varies linearly with VC, and only when VVC is very small. And as VVC increases, IC becomes constant. Here, VVC is independent of IC, and actually we have base collector junction, base collector connection, that is output circuit, and in output characteristics curve, if we increase the base collector voltage, then uh, IC becomes constant. And input and output resistance of common base configuration, that is input resistance and output resistance, and the ratio of the emitter base voltage to the change of the emitter current is called input resistance, and the ratio of the change of the base collector voltage to the change of the collector current is called output resistance. And in common emitter connection, here look, this circuit is little bit different to the previous circuit, and previous circuit is discuss about common base. In previously, base is connected with collector and base is also connected with emitter, but here collector emitter is common, and that's why emitter is connected with here IE. This terminal is emitter, and a emitter is connected with base, and emitter is connected with collector. And then here for common emitter connection, this is for PNP, and this is for NPN transistor, and both the circuit is for common emitter connection. And for common emitter connection, we have current amplification, base current amplification factor, that is denoted by beta, and this is the ratio of the change of the collector current to the change of the base current, that is beta is equal to del IC divided by del IV. And normally only 5% of the emitter current flows to base, so amplification factor is greater than 20. Usually this range varies from 20 to 500. And the relation between alpha and beta, and already we have this equation that is for alpha and beta, and I is equal to IB plus IC, and we all know all these equation, that is uh, for uh, um, that is for uh, that is for beta, alpha, and total current, that is emitter current IE. And here IE is emitter current, and del IE is also emitter current, and that is this equation for AC current, and this equation is for DC current. And uh, from this equation we know del IB is equal to IE minus del I minus del IC, and by putting this value in the equation for beta, that is IC equal to IC plus del IC divided by del IB, by putting this value, and finally we divide all this term with del IE, Then divided all this term with del IE, we have the equation that is beta is equal to alpha by 1 minus alpha. Here, this is the relation for this is the relation for alpha and beta, that is beta is equal to alpha by 1 minus alpha. And here, for expression for collector current, previously we have discussed this, that is IC is equal to alpha I plus ICVO, that is I is equal to IB plus IC, and by putting the value of collector current to the equation, I E is equal to IB plus IC, and finally by calculating we can get the equation for emitter current, that is IE is equal to beta plus 1 into IB plus beta plus 1 into ICVO. Here emitter current is dependent, emitter current is independent of collector current, and here is based on base current and leakage current. Here leakage current is ICVO. And the characteristics of common emitter connection. For common emitter connection, here the input circuit is base emitter circuit. Here the curve is discussed between base emitter voltage versus IB, um, is called input characteristics, and IB increases rapidly with VBE. It means input resistance is very small, and here I is almost independent of collector emitter circuit, and IB is in the is of the range of microamperes. And output characteristics, these are the curve for output characteristics, and by observing this curve here, the graph is shown for VCE versus IC. Actually it's also a characteristics curve for IB characteristics curve, and here the base is here. Characteristics of common emitter configuration, IC varies linearly with VCE, that is a common emitter connection. Voltage in common emitter connection only when voltage in common emitter connection is very small. As VC increases, IC becomes constant. And input and output resistance of common emitter connection. Here, input resistance is the ratio of the change of the base emitter emitter base voltage to the change of base current, is called input resistance. The ratio of the change in collector emitter voltage to the change in collector current is called output resistance. And here third type connection is common collector configuration. In common collector terminology is derived from the fact that the collector is common to both input and output side of the configuration. Here collector is connected with base and collector is also connected with emitter. That's why this connection is called common collector configuration, and this is applicable for both PNP and NPN transistor. And here base collector is input terminal, and emitter collector is output terminal and output circuit. And in common collector configuration, is current amplification factor is denoted by gamma. And here IE in common emitter connection, input current is base current and output current is emitter current, and the ratio of the change in emitter current to the change in base current is known as current amplification factor, and this is denoted by gamma. And here in this circuit, in uh, common emitter configuration, del IE is nearly equal to del IC. And here the relation between alpha and gamma has derived, and previously we discussed about the alpha and gamma, and here gamma is equal to del I by del IB, and alpha is equal to del IC by del IE. And we know the equation for I is equal to IB plus IC for DC current, and for AC current we have the equation that is del IE is equal to del IE is equal to del IB plus del IC. And from this equation we can write del IB is equal to del IE minus del IC, and by putting this value in the equation, that is for gamma is equal to del I by del IB, and here the equation is gamma is equal to del IE divided by del IE minus del IC. And by dividing these we divide all this term by del IE, and we have we have this uh, have this 1 by 1 minus alpha, and this is the relation between gamma and alpha. And the equation, final equation is gamma is equal to 1 by 1 minus alpha. And expression for collector current, that is IC is equal to alpha I plus ICVO, and here the ICVO, that is for leakage current, and by putting this value of value in the main equation, that is I del I is equal to IB plus IC, by putting this value we have uh, mm, uh, we have this IB plus by putting this value of IC in the second line, we have IE is equal to IB plus alpha IE plus ICVO. And after calculation, calculating, we have the equation for IE is equal to beta plus 1 into beta plus beta plus 1 into ICVO. And finally, we have the equation that is beta is equal to alpha by 1 minus alpha, and or beta is equal to uh, beta plus 1 is equal to 1 by 1 minus alpha. And comparison between transistor connection, we have three connection, that is common base, common emitter, and common collector. And here input resistance for common base is low, and the value is shown here for input resistance, that is 100, and for common emitter there is 750. And uh, for common collector connection, the input resistance is very high. For common base correction, output resistance is very high, but for common collector correction, output resistance is very low. And voltage gain, that is 150, and here the voltage gain is 500, and here the voltage gain is less than 1. And application is for high frequency application, it's for audio frequency application, it's for impedance matching. And here current gain, there is no current gain, there is less than 1. And here for common emitter correction, current gain is high, and here the current gain is appreciable for common collector connection. I think these table will be very helpful to understand the inner characteristics of uh, uh, common base, common emitter, and common collector connection, and this is the comparison among them. And here the characteristics are input resistance, output resistance, voltage gain applications, and current gain. All these terms are all these characteristics discussed among these CB, CC, and CE. And here transistor, we can use transistor as an amplifier, and here that is in common emitter connection. And in common emitter connection, and we explain this for a NPN transistor, and here the battery is VVV is connected with base in order to make base forward bias, and regardless of input AC polarity, and output is taken across the load. And here for a small signal we get a large signal in output terminal. And here emitter base circuit is input circuit, and collector emitter circuit is output circuit, and we take the output across a load resistance, and finally we got a output current that is much more larger than the input current. And this is the property um, this is a property of amplifier. And we used transistor as an amplifier in these we use transistor as an amplifier. And here the connection is common emitter configuration. Here the connection is common emitter configuration. And during positive half cycle, input AC will keep the emitter base junction more forward bias, so more carrier will be emitted by emitter. This use current will flow through load, and we will find output amplified signal. And during negative half cycle, input AC signal will keep the emitter base junction less forward bias, so less carrier will be emitted by emitter, hence collector current decreases. This results in decreased output voltage, that is in opposite direction. I think these two half cycle, that is positive half cycle and negative half cycle for input AC signal for emitter base junction. For here the difference is for positive half cycle forward bias is more, and for negative half cycle forward bias is less. That's why we get a amplified signal in output. And we can transistor here. The RC is the load resistance, and transistor load line. In transistor load line analysis, we consider common emitter NPN transistor as circuit shown in the figure, and there is no input signal there is no input signal in base emitter circuit. And we apply Kirchhoff voltage law in the output circuit, and we already know already know about Kirchhoff voltage law from chapter 3, that is current electricity. And by applying Kirchhoff voltage law in the output circuit, we can write VCE is equal to VCC minus IC RC. And here the collector current is IC is 0, and collector emitter voltage is maximum and is equal to collector emitter voltage is maximum and is equal to VCC, that is VC is equal to VCC minus ICRC. And by putting this value, we have collector emitter voltage, that is VC is equal to 0, and hence we finally have the equation for maximum current, that is IC is equal to VCC minus by RC. And in load line analysis, look at this curve, and Q is the here Q point is the Q point or Q factor is the active transistor mode. And with the increase of voltage, current will decrease in decrease. And we have we have an intersecting point that is called a Q point, or that is also known as operating point. And zero signal values of IC and VCE are known as the operating point. And it is called operating because a variation of IC takes place about this point, and it is also called quiescent point or Q point. And here the necessary equation is shown for you, that is IC is equal to IB plus IC, del IC is equal to del IB plus del IC. And here three equation for alpha, beta and gamma is shown, and the relation between gamma and alpha is shown in the left side of the screen. Here gamma is equal to 1 by 1 minus alpha. This is the relation between gamma and alpha. I think you may have some question regarding to our topic, and if you find any difficulties, then ask me in our class time. And these all are the home task for you. That is, you have to explain the concept of hole and readiness equation of this chapter, and draw 3 diagram, that is common base, common emitter, and common collector transistor. Hope that all of you are fine despite uh, corona pandemic. Be conscious about COVID-19 and take necessary steps like wear mask and wash your hand frequently, and stay home, stay safe. Thank you all for joining with us. That's all for today. Allah Hafiz.